Hello students, welcome back to the world of waves. We were discussing about different aspects of waves. Okay, and today we will discuss about energy flow taking place in a wave. Means wave is a method to convey or transfer energy from one place to another place. Okay, and in that oscillation, medium whichever medium through which the wave is passing, medium is continuously undergoing some motions. They undergo oscillatory motion. Okay, and similarly the medium undergoes some sort of deformation because they are moving. For example, if you consider a string, every particles of the string is moving up and down, making to and fro motion. Similarly, the string is undergoing some sort of deformation. So deformation means the shape is changing, or the string is undergoing some pressure. So its shape is changing. So there is a associated force, there is an associated energy. Okay, so we are interested to calculate the energy propagating through a wave by knowing the amplitude of the wave, by knowing the frequency of the wave. Okay, there are such features for a wave. Using such parameters, the total energy propagating across a wave can be calculated. Okay, so you know that whenever a wave is propagating through a medium, all the particles of the medium are in motion. Okay, the main motion that we can see is the oscillatory motion. Every particle oscillates successively or synchronously. That is how the motion is transferred from one place to another place. And particles at any time instant, if you take any time instant, the particle occupy different states of motion. Okay, some particle may be in the extreme position, some particle may be in the equilibrium, and some particle may be in the other side of the oscillatory motion. So you can see in this graphics, okay, each and every particle is oscillating at a different time instant. Their position, their states are different. That is what is meant by the statement. And all the particles are in one of the states of oscillating motion. That is what we told. And another thing is that when they oscillate, they are not merely oscillating; they are helping the wave to transfer energy from one place to another place. Okay, suppose the first oscillator, the first particle is oscillating. It is not merely oscillating with its energy; that energy is getting transferred to the next particle, and next particle transfer the energy to next particle. So and so forth goes on. Okay, as a result, the energy is getting transferred. Okay, so that is shown in a more clarified way here. You can understand. So in totality, the wave motion is a composition of a number of simple harmonic motion. Especially for a plane harmonic motion, it is composed of infinite number of simple harmonic motion, which happens in a synchronous way, in a periodic way. So the energy gets transferred, and due to the up and down motion, what happens? The particles of the medium get energy, because they are moving. So moving energy is called kinetic energy. And as the wave propagates, the medium undergoes certain kind of deformation also. This is another thing, because suppose you take a water wave. When water wave propagates, the water is getting compressed and elongated periodically. So there is some compressive force associated with it. So we are also interested to calculate the potential energy, kinetic energy. So we can calculate the total energy of the wave. For which what we do is, we will take a small portion of the medium or a string, then we will calculate potential energy, and kinetic energy separately. Then we will add up. So we will get the total energy for a small elementary section of the string or medium. Okay. Then we will apply. Here we are more particularly interested to calculate the energy of a sinusoidal wave. Okay, we are mainly focusing on sinusoidal. No other wave is taken here. Only sinusoidal waves are taken. You know there are so many different types of wave: spiral wave, triangular wave, okay, and Gaussian wave, pulses, so and so forth. Many examples are there. But here we will focus simply on sinusoidal wave. We are interested to calculate the total energy. And once we calculate the total energy for a small section, then we can find the total energy for the entire wave, and that can be used to calculate rate of energy propagation along the string. Understand? So from small piece to the whole string we will extend. Throughout this discussion we will be using string. Okay, you can imagine it as a medium, but we will talk in terms of a string, a small wire connected, and that wire is oscillated, You can oscillate a wire. Suppose this is a string or a wire or a rock. You can give some vibration with some machineries. So vibration will move on, okay, as shown in this animation. And in which what we are doing is we take a small segment on this rock, small segment, say some length delta x. Then we will find this kinetic energy first. Then we will find this potential energy. Then we will add it up. Okay, we will get the total energy of this small segment. Then we will find the energy for the entire string. Then we will find the average energy flowing through this string when it is oscillating. It is obvious that energy is continuously fed from here, and that energy is not getting accumulated here. It is not getting still here. It is propagating forward. Okay, so that concept should be there. That is a methodology we have adopted to find the energy flow through a string. So we will consider a small string, okay, as shown in the figure. So this is magnified. A magnified picture of this thing is shown here. We have a small string of some length, say dx. Okay, so this is a magnified view. In fact, this is the picture, and in which we have taken a small segment, a small piece cut away, and its kinetic energy, potential energy will be calculated and we add. So we consider a small segment of string of length delta x, say at a distance x from the origin. Okay, so that we can do, and you imagine that the string is of linear mass density mu. That means mass per unit length of the string, let it be mu kilogram per meter. You can find it easily. What you have to do, you weigh the string by putting in some weighing balance, you will get the mass. You measure the length of the string, you will get the length. You divide the mass with the length, you will get a linear mass density. That is mu. So if the linear mass density is mu, then the mass of this small segment is simply mu into delta x. Understand? Mu into delta x. So you can write a delta m is equal to mu into delta x. So no problem. So that is there. Why do we need this mass? Because we know that for calculating kinetic energy expression is half m square. So we need this mass. So we got the mass of this segment, that is mu delta x. And now since it is oscillating up and down, the vertical velocity of this string at any instant you can find if you know the displacement. If you know the function y, okay, how y varies with time, if you know, you can easily find the vertical velocity. In general, you can write velocity, vertical velocity is shown with uy equal to del y by del t, a partial differential of y. Understand? Because y is a function of time. By differentiating y, you can find velocity at any instant. Okay, vertical velocity at any instant. Okay, so once you have uy, you have mass, then we can easily find Now you can easily find the kinetic energy, because kinetic energy is half mv square. So we can find the kinetic energy of the small piece. So that is shown as dk. dk means a small kinetic energy, possibly the small piece. So half into mass is dm into uy square. Dm already we have written, dm is equal to mu into dx, and velocity is dou y by dou t. So you can put all these values here. So you get the small kinetic energy possessed by small piece dx, that is equal to half mu dx dou y by dou t whole square. Okay, and you know that this is a instantaneous kinetic energy because there is a time here. So obviously, as we did in vibration, you can easily find the average kinetic energy, but we will do it later. And its value is time dependent. Understand? Now we will find potential energy, then we will add up, then we will find average energy. That is the more easiest way. So let us keep it like this. This is the kinetic energy possible by small piece. That is why we have placed a D here. Understand? We have placed a D here. Okay. So we have the kinetic energy. And if you know the wave function, how the y depends on time, usually we write it like this: y of x is equal to a sin x minus omega t. We have already done. So you can put this y here. You can differentiate y with respect to time partially. So when you differentiate partially with respect to time, what we get? Omega is here. So minus omega a cos kx minus omega. So we got del y by del t or dou y by dou t. So kinetic energy can be found by putting dou y by dou t here. So you have minus omega a cos kx minus omega t also. You can square it. You can write the kinetic energy expression for a sinusoidal wave. Okay, we are focusing on sinusoidal wave. So for a sinusoidal wave, you borrow the expression for kinetic energy. I hope this idea is clear. Now let us find potential energy of the segment. Okay, potential energy. How you will find it? You know, string is oscillating up and down. So there is some deformation to the string. As a result, the string length may be increasing slightly because string is moved up and down. The actual length is x, but when it is moved up and down, string is getting elongated, compressed like that. So there is a change in the length of the string. Change in the length of the string. So due to the transverse movement, length is slightly increased. Length is slightly increased. So that leads to deformation of the string. Deformation means change in length. Change in length. So due to this change in length, a restoring force is developed in the string, which sets up potential energy. Understand? So whenever we compress or elongate something, potential energy is developed in the string or in any material. For the time being, we have a string here. So in string, potential energy is developed. Okay. So potential energy of the string can be found by the following method. You know that potentially developed in the string can be found. We know the string is under tension because we have kept it pulled by adding some weight at one end. So string is kept vertically, so there is a tension. So the potential energy developed in the string will be equal to tension multiplied by change in length. It is something like a force into displacement, isn't it? Force is tension here, change in length is displacement. You know potential energy is equal to force into displacement. Whenever we lift a body, force multiplied by displacement will give you potential energy. Same idea. Here T is the force undergone by the string, and we are changing its length by vertical displacement. So there is a potential energy development. And what is the change in length? We can easily find it. We can find the change in length from the figure. This is the original length dx for a small piece. Okay, imagine this is a small piece of string. and when it is stretched up, this new length is ds. New length is ds. Understand? So the changing length will be ds minus dx. Ds minus dx. So we got the potential energy of the string for a small length dx. And from the figure you can see, what you can see, this is almost a right angle triangle. So from the figure you can see that ds square is equal to dx square plus dy square. Dx square plus dy square. So you can write ds is equal to dx into 1 plus delta y by delta x all square or raised to 1 by 2. Very simple. You take dx outside. You can even show with a dy by dx, no problem. But here we are taking only the x dependency. Time dependency is not taken. So that is why we are written dou y by dou x. There is no problem even if you write dy by dx. Okay. Yes, I modified this equation and I wrote it like this. This is a simple procedure. Okay. So our aim is to find the ds minus dx. We want to get the ds minus dx. So we found the ds is this. Again, you can expand it. You can expand it and we can simplify it. This expression. For that we will be using binomial theorem. We know binomial theorem says that 1 plus x all raised to n. You study in mathematics. 1 plus x all raised to n is equal to 1 plus nx plus n into n minus 1 by 2 factorial x squared. So it goes on like that. I am not interested in higher terms because we may not be using it. But it is the expression. In our current equation, in this equation, you know that what is the dx? X is equal to dou y by dou x all square. Similarly, you have n here, n is equal to 1 by 2. N is equal to 1 by 2. These two things are known, so you can just substitute, you can expand it. You can expand 1 plus dou y by dou x all square all raised to 1 by 2 is equal to 1 plus, first term is nx, n is 1 by 2, x is dou y by dou x all square, and similarly second term. We can write like this. But we know that since the string is oscillating very fast and vertical displacement is small, so dou y by dou x is much lesser than 1. Whenever you have seen the string vibration, it is very fast happening, and the height or the vertical displacement is not too high. Whenever you do the experiment in lab, you might have seen that this oscillation is very fast. So the change in y is small, so dou y by dou x is also very small. So much less than 1. So we can say that we can avoid higher terms containing raised to 4, containing raised to 8, like that. Terms we can neglect. So expansion can be made more simple. You see, only the first and second term is kept, remaining terms are removed. So now we have a simple expression 1 plus 1 by 2 dou y by dou x all square. We expanded using binomial theorem because we need it. For we need it, we know ds is equal to dx into this one. Okay, this one we found out. We can use it. This one we reduced in this form because left hand side contains powers and all. It is a complicated thing, but we simplified like this. So now we can replace our 1 plus this expression. So now we have ds is equal to dx into 1 plus 1 by 2 dou y by dou x all square. You can use this expression to find the potential energy. Okay, you can use to find the potential energy. ds by dx, we were trying to calculate what is ds new length, original length. So change in length. You can get it as ds minus dx is equal to 1 by 2 dou y by dou x whole square dx. So you can put here now, no problem. Ds minus dx you can substitute. What we get? Yes, tension into 1 by 2, all the things. Okay. So we found this way the change in potential energy of the string. Change in potential energy of the string we got. Okay, we can modify it and write take 1 by 2 initially, then t, then dou y by dou x whole square into dx. So we got the change in potential energy of the string. And this is the sinusoidal expression of the wave as usual. And here also we have a y here, dou y by dou x. So you have to find the dou y by dou x now. Very simple. Differentiate the given expression with respect to x. So differentiation comes for kx. So k can be taken outside. So we have dou y by dou x here. Dou y by dou x. That can be placed here. Dou y by dou x can be removed and replace this value. Square it. So we get the change in potential energy for a small segment dx. Understand? Earlier we found kinetic energy expression for dx. Currently we found potential energy expression for dx. Understand? So now we can find the total energy of the segment dx. Okay. Our length of the segment is string segment is actually dx. So we have dk, we have dpe. We can add it up. So we get the total energy of the string. So it seems to be complicated, but not in fact. You can make it very simple. How you take the cost per term outside and many other common terms outside. So you can see now that by taking all the common terms outside, inside the bracket now you have mu omega square. What is mu? You know, mass per unit length. Omega is angular frequency, and T is tension on the string, and K is the wave constant. You want to give number and all. So we got a total energy expression. We can simplify it a little bit more. How inside the bracket you have mu omega square and pk square. You can make some adjustment. We know tension and velocity is raised like this. We have written that velocity is equal to root of t by mu. I hope you remember it. So we have in the previous video we have derived it. Okay, so we can write it, tension we can remove with this equation, and velocity is also written as omega by t. Is also derived. So put it the value here. So t you can write as omega square by k square mu. Okay, you can put it here. So what happened? T removed. We substituted for t. So here k square you can cancel. So what is left is mu omega square. Again mu omega square. So 2 mu omega square. So there is a 2 here and there is a 2 here. So both 2 we can cancel. So now you have d is equal to k square mu omega square k square kx minus omega t dx. Okay. So we have now the expression for the total energy. Okay, total energy crossing through a surface or a plane, we can say, or a plane, or passing through total energy possessed by a small segment dx is given here. A small segment dx is given here. Okay. Energy, then this is the energy possessed by dx length of the string, dx length of string when it is oscillating. If you divide both sides of the equation with dt, what we will get? When you divide both sides of the equation, you will get the energy flow rate of energy flow, or instantaneous rate of energy flow, because continuously energy is flowing across the string. So we cannot say that energy is staying somewhere, sustaining somewhere. No, it is continuously flowing out. So dE by dt will tell you a physics. What physics will tell you? It tells at what rate energy is going across the string. So we differentiated or divided dt on both sides. Understand? Oh, and dx by dt is what? Dx by dt is the velocity with which the wave is propagating. D now. Dx by dt is the velocity with which wave is propagating. D by dt is the power. You can call it power, instantaneous power. Why it is instantaneous? Because there is a time here. So instantaneous power, and dx by dt is the velocity. So you can put these two values here. So what we get? We get instantaneous power crossing through the string is equal to a square mu omega square 4 square x minus omega t in the mean. Okay, other things are already there. No confusion. But there is a problem. It is instantaneous. That means every instant this power changes. Such a value we cannot measure physically. We cannot experimentally measure it. And if you want to measure it experimentally, you have to find average of this power. How you will get it? Yeah, you divide this with period, total time. Then you will get the average power. That can be measured, and we have done such a procedure in simple harmonic motion. I hope you remember. Average kinetic energy will be calculated, average potential energy will be calculated. Similarly, here also the average power crossing through the string you have to calculate. So for we have to divide. First you find the total power for every time instant over a complete period. Okay, this is instantaneous power. No physical meaning. We cannot say no meaning. No physically valid meaning. So what we did is you find the total power over a cycle. Understand? Total power over a cycle. Then divide it with the t. So you get the average power that is physically meaningful. That can be done. Okay, so that we will do. Very simple. How to do? Yes, you integrate this sine function. Many terms are constant. You can take it outside. Many terms are constant. You can take it outside. So now integrate cos square dt. And you know very well that when you integrate cos square dt over a complete cycle, we have done it many times. You will get simply t by 2. You will get it simply. Anybody can check it. You know it. So we can substitute this value here, t by 2. So putting the t by 2 here instead of the integral, you can cancel this tt now, isn't it? You can cancel. You get the average power expression. That will be simply 1 by 2 mu v omega square s. There is no sine term, there is no cos term, there is no time dependency. Purely a constant, isn't it? No time dependency. Mu is a constant, velocity is a constant, omega is a constant, a is a constant. So if you know all these parameters for a string wave, you can find the average power. It's a measurable quantity. It's a physically meaningful quantity. Understand? And graphically these are shown here. Y displacement is shown here. This is a time dependent quantity. Energy, instantaneous energy is shown here. This is also a time dependent quantity. But the power, the average power you have calculated is a constant one. It is graphically shown here. Okay, we can also put the equations here. 3 equations for one for y, one for instantaneous energy possessed by the different segments, and finally you have the power. You see, power is a constant, so it is a measurable quantity. Something which is instantaneously changing, we cannot measure using a device. But if something is constant or steadily remaining value, so that can be measured using a device, and this is a measurable quantity. What is the physical meaning or the physical intuition of this idea? This is the energy crossed across any vertical plane at right angles to the direction of propagation of the wave in unit time. Understand? The average power will give you what? The energy crossed across any given surface in unit time. Understand? Any wave you consider, this expression will give you the total energy crossed through any plane in unit time. Okay, you can talk about electromagnetic wave or heat wave or any type of wave, mechanical wave crossing through a string, or even sound wave. Suppose you have a musical system continuously producing sound, you can find the total power produced by the audio system. Okay, usually the power of a wattage of a audio system is shown here. It shows how much energy it is radiating out into the space in a given unit time. As the power of the audio system increases, the the higher or the more will be the sound effect is produced in the surrounding space. Understand? So overall, this concept is valid. Okay. So average power is a very physically meaningful quantity, and power higher means amplitude higher. In case of sound, you can get more impact when power is high. That we usually experience with a sound system. The greater the wattage or power, the greater its sound effects. Okay, it's one of the instantaneous examples that we can plot. So we have already said that instantaneous power is a time-dependent quantity which is not measurable. Okay, but average power is a measurable quantity and it's physically more meaningful, and that we have calculated. And what physical intuition we get about the power, this is that the average power is the energy that must be fed to the string so as to maintain a continuous oscillation having a frequency omega and amplitude A propagating with velocity v. This is very important. This power is nothing but this is the power or energy in unit time that must be given to the string so as to maintain the oscillation with the same amplitude. Understand? This is the physics of that. Every instant, in every unit time, you have to feed the string with this much of energy. If you don't give this energy, the string will stop oscillating. Understand? String will stop oscillating. So this expression gives an idea about how much energy I should give to a string so as to maintain a oscillation with a given frequency with a given amplitude. Understand? So these are the most important point is this must be understood thoroughly. I hope these ideas are clear. You have to watch this video at least twice to get the entire physical concept. One of the important videos. And here is a problem for you, physical problem now given. A long string is connected to an electrically driven oscillator so that a transverse sinusoidal wave is propagated along the string. Very simple, we have already discussed it. The string has a mass per unit length of 30 gram per meter linear mass density and is held under a tension 12 Newton. Okay, linear mass density is given in CGS system, not down it. You have to convert into SI system. Question number 1 is calculate the power that must be supplied to the oscillator to sustain the propagation of wave if it has a frequency of 150 Hz and an amplitude of 1.5 centimeter. You can calculate it, no problem. You can do it. Question number 2. What will be the power required if the frequency doubled? Okay, you can find it. You know the equation, you can find it. Similarly, what will be the power if the amplitude is half? If the amplitude is half. It's a very typical question, likely to be asked in any university level examinations. So please do it sincerely. Okay, the answers are given here. The likely answers are given here. It is only for your help, or to do independently with the drawing all the figures and all. Okay, all the figures. Once again, you are reminded to watch this video twice and make a complete video note, lecture note. Okay, you can try to get the best possible idea about the derivation we have made here. Then only you have to attempt for solving the problem. Okay, I hope you enjoyed this video. You represent your appreciation in the YouTube channel with suitable comments, supporting comments. You represent. So, with these words, let us conclude today. Thank you all.